Hello again, Miss Denton here, and in this video we're going to be looking at and studying rectangles, okay? So this is your third shape in the quadrilateral series. We've looked at parallelograms, and if you notice, a parallelogram is like a squished over rectangle. It's like we took these 90-degree angles and we started flattening the shape. We've also looked at a rhombus, which it seemed very similar to a square. A lot of students say it looks kind of like a square and a parallelogram put together, and they're exactly right. So our third shape here is a rectangle. So by now, I really hope that you are comfortable with the tools. So I'll do a couple measures with you, then I'm going to pause the video and let you finish out some measures. So let's start with some of these exterior sides. Again, I'm going to measure in centimeters, okay? So I'm going to start up with AB, get a good read on AB. I'm getting like 13.7. I'm going to use 13.7. Okay, and I'm going to go for AD next. Looks like 6.4-ish. And I'm going to pause the video and you write in the other side measures of these exterior pieces. Okay, because we know that the opposite sides of all our parallelograms are congruent, that holds true for rectangles too. And you have known that since you were in like second grade, so don't overthink it, okay? You know these two have been congruent for a long, long, long time, so that doesn't change just because we're getting more detailed. Okay, what I want to challenge you to do next, instead of using the ruler to measure the diagonal, okay, I want you to notice something else that you've known about rectangles for a long time. You have known forever and ever and ever, it seems like, that the corners in a rectangle are perfect 90-degree angles, right? You've known that. I'm not going to treat you as silly, like dumb children. You are absolutely not. You've known that for so long, and that's not going to change. So the reason I'm pointing that out is because look here. Now we have this giant right triangle packed into our rectangle. And we know on a right triangle that we should be using Pythagorean theorem. So instead of getting a pretty good measurement using my ruler, I'm going to get an awesome measurement using Pythagorean theorem. A squared plus B squared equals C squared. So take a minute using the measures we already have and find that diagonal. All right, let's check it out. I've got my work over here for Pythagorean theorem. 6.4 for leg A, 13.7 for leg B. Square them, add them together. I got 228.65. That equals the hypotenuse squared. So if I take the square root of that, I get 15.1. Let's see if that's what I would have gotten if I had used my ruler to measure from A to C. Ooh, what a good measure. I might have gotten 16.1. I also might have picked 15.2. Just depends on my eye. So when we're doing this by hand, there's a lot of room for just simple error. If I slide it this way just a little, it might be 15.1. If I slide it the other way a little, I might have picked 15.2. You know, I've got a thick line there. It would be hard to tell. But by using the Pythagorean theorem, I know that that is absolutely correct. Okay, well, check this out. Grab this ruler real quick. To measure from B to D, notice that you're also right there on that 15.1, 15.2 line. And I hope that's not a surprise to you. Let's think about that. If I were to highlight another right triangle using angle A as my right angle, okay, I'd be looking at this shape. That's another right triangle, and I'd be using 6.4 for the A and 13.7 for the B, so I'd be doing the exact same work on this diagonal. So hopefully that makes sense that they're both 15.1 centimeters. Okay, now what have you learned about point E here in the interior of the shape throughout our study so far? What have you learned? Think about it a second, or flip back to your other pages. What does that point E do to the following diagonal measures? Okay, I hope you thought of E as the midpoint. E is the midpoint of these diagonals. So if E's in the middle and you cut that diagonal in half, I got 7.55. So that's going to be the measure of each of these pieces of the diagonal. Now, would I get 7.55 if I measured with my ruler? No, I would not. I would probably just say 7.6. And again, that's just a user error, or if we move our ruler just a little either direction. But the exact answer would come from this cut. While we cut the diagonal in half, we get 7.55. So check this out. Now, something new is happening. Something different. Let me grab my old shape. Okay. In our previous shapes, E was the midpoint, but it didn't make 4 equal pieces of diagonal. It made a midpoint, so 5.2, 5.2 here, and 4, 4 here. It's not all 4s or all 5.2s. That also happened on our parallelogram. E is the midpoint, but it made different measures for each slice. Now in a rectangle, E is the midpoint, and it makes every little slice equal to each other. This is a very symmetric shape. All right, let's move on to angles. We've already got our 90-degree angles in the corner. Now I think we're going to start right here at the intersection again. AEB. Let's check that out. AEB is this upper obtuse angle. So let's line up our protractor. Nice and flat. I have AEB obtuse, so I'm counting the insides the way I've held mine at 130, looks like 132 degrees. 132 degrees. Okay. Well, I want you to take that 132 degrees and find the 3 other angles here, this first row, find the rest of those angles. All right, how'd you do? I used my vertical angles. If I got 132 for this obtuse angle up top, transfers below. Then I use my linear pairs. I know an obtuse and an acute side by side have to add up to 180 degrees. So I got 48s for the others. Now, for my other angles, I could grab my protractor. That's something I could do, especially if I'm a very concrete person. I can grab my protractor and measure any of the 8 angles I have left. But because I'm dealing with a right triangle, I challenge you to use something else that has to do with right triangles, like right triangle trig, SOHCAHTOA. Let's just give it a shot. We can check our answers with the protractor. So I'm going to go for this angle here. I'll call this my theta from right triangle trig. I'm going to use the 13.7 that I measured. That would be the opposite. And the 6.4 I measured. That would be the adjacent. I'm not going to use this hypotenuse. And my reason that I'm not going to use that is because I had to solve for the hypotenuse with the Pythagorean theorem over here. And if I made a mistake here and got the wrong answer, and then tried to use that value Here, I would have a double wrong answer. So I'm going to go with the two that I measured, the opposite and adjacent, which is a tangent trig value. So I'm going to say tangent of theta, which is the angle I'm trying to find, is equal to the opposite value, 13.7, over the adjacent value, 6.4. To find theta, I need to apply the tangent inverse. Anytime I want to find an angle, I'm going to be using the inverse trig value. Take a moment, use your calculator, and solve for theta. All right, check it out. I got 64.96 degrees, a very, in fact, I got more than that. I got 64.96021568, blah, 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 blah. So this is a very exact measurement. Let's see what I would have gotten had I used my protractor. Line this up down here. Follow the diagonal. There's the 60. And check that out. I am right at 65 degrees. So I would not have gotten 64.96. No way. I've just got a simple protractor here. But I would have gotten right at 65 degrees. So I'm going to go ahead and round that to 65 degrees for the purpose of the rest of this worksheet. That is angle BCE or ECB. So I thought that was a great example of how your right triangle trig may filter into what you do, as well as the Pythagorean theorem. Okay, well, let's use that 65 to finish up this highlighted triangle, right? We've got this big right angle that we've highlighted. Remember, a triangle holds a total of 180 degrees. So in this 180 degree triangle, this yellow triangle, we've got our 65 degrees down here in the corner that's used up, and the 90 degree angle at angle B, leaving us with 25 degrees up here in the acute portion of this 90 degree. That is BAE, or reverse it, EAB, angle EAB, 25 degrees. And guys, we're done with any measurements. Whether we're done with the trig or we're done with our protractor, we're done because we can use everything we know about this shape to finish it out. For example, if I wanted to find the other portion of this 90 degree angle, this is a complementary set, two angles that add up to 90. Well, 90, take away the 25, leaves me with 65 for this portion, which in fact is an alternate interior to the 65 I already solved for. The same thing can be done here. This 25 is an alternate interior with the other portion of this 90 degree angle. So I've got a couple more angles in there. Let's write them in. I've got EAD at 65 degrees. EAB at 25 degrees. Do I have EBC yet? Not yet. Come back to it. ECD, 25 degrees. EDC, EDC, not yet. And EDA, not yet. Okay, so I have three angles left. Let's take a look. I'm going to highlight a different triangle now. Grab a pink marker here. Check out, let's do this triangle. Check this out. This triangle hiding right here will make this pretty easy for us. Within this triangle, which is a total of 180 degrees, we've used 132 and 25. So we've already used that up. Whatever's left could be this acute angle here. So 180, subtract the 132, subtract the 25, what's left? a 23-degree angle. Use that alternate interior. Flip it on over there. You'll have another 23-degree angle. And these two angles have to add up to a total of 90 degrees. So complementary, 90, take away that 23, it's going to leave me with 67 in either position. Now, I have to admit something, which is why I paused a moment ago. Something is a little off with one of my measurements, and here's why. Think of what you know about a rectangle. A rectangle is perfectly symmetric. So, if I were to take this rectangle and draw a line of symmetry here, okay, I'm running out of colors. I think it's going to get real busy. If I were to draw a line of symmetry right down the middle, then everything on the left should match up with everything on the right, and it doesn't. Boom. I got a 25 matching with a 23. That's not okay. I've got a 65 matching with a 67. That's not okay. So, gosh, something's not matching up. I know I used trig to solve for that 65-degree angle. I know I did some rounding, but I know the trig's not going to lie to me. So if I want to go with the most accurate measurement, I'm going to take this 65-degree angle and transport it across that line of symmetry. I'm going to change this to 65. Okay, the same thing would happen here. This 65-degree angle would transport across and change the 67 to a 65. Now, I could use that 65 to help me adjust this 23, and lo and behold, here's another line of symmetry coming across a rectangle, because I could fold this rectangle up this direction and everything would match up. So this 25 would transfer up, and this 25 would transfer down. Now, what else might that change about my shape? Okay, don't give up on it. I've got two 25s and a 132. Something's wrong. The reason I know something's wrong is because they don't add up to 180. 25, 25, and 132 adds up to 182. So this is an angle that maybe I misread when I was using my protractor. If that was 130, 25, 25, and 130 add up to 180. And I can make some adjustments all the way around. My vertical angles could change. My linear pairs could change. They'd have to be 50 degrees. Now, I'm not saying that we're going to be perfect every time. Obviously, we're not. Maybe, just maybe, these aren't 13.7 and 6.4, which I used here, which gave me this answer, which we changed everything to match. But we do want everything to read together wisely. Okay, we don't want our angles to not add up to 180 degrees. That breaks a fundamental rule of all of our triangle sum theorems, okay? We also don't want our right triangle trig to not work out. We don't want our Pythagorean theorem to not work out. We want everything to work that is a principle of geometry. So if that means going back in and changing a measure, that's absolutely fine, because this is the one thing that we might not be perfect at. And now that I'm reading it again, that 130 is spot on. That definitely could have been a 130-degree angle when earlier I read it as 132. So just realize, guys, I'm not asking for perfection. I just want everything to speak to each other, to follow the rules of geometry. I'm going to make some adjustments down here. AEB, I got 130. BEC, I'm changing that to 50. 130, changing this one to 50. These I all based off the trig, so I'm keeping that. And how did we finish it out? EBC, 65. EDC 25, EDA 65. I've got my lines of symmetry, I've got my right triangles, my complementary angles in the corner, my trig values work out, my Pythagorean theorem values work out. This is now a really solid measure of this rectangle. Let's use this rectangle and highlight the truths down here. Ready? All right, let me zoom out just a smidge. Okay, both pairs of opposite sides parallel. Yes, they are. Both pairs of opposite sides are parallel, not just one. Both pairs of opposite sides are congruent. 6.4, 6.4, 13.7, 13.7. That's a yes. Not only one. Both pairs of opposite angles congruent. That's a yes. 90, 90, 90, 90. Not just one pair. However, this time all four angles are congruent to each other because they're all 90s. Also, something new for the rectangle that hasn't shown up before, all the diagonals are congruent to each other. They also bisect each other, 7.5, 7.5, 7.5, 7.5. They are not perpendicular. We've got our 130 degrees and our 50 degrees. And they do not bisect the angles of this figure. This 90 degrees was split into 25 and 65. That's not a bisection. Oops. Okay, so let's freeze for just a second. I'm going to show you something. We started with a parallelogram. Our parallelogram had these four features that were true. When we moved on to a rhombus, those four features remain the same, and we added in these two features about the diagonals. Now that we've moved on to a rectangle, the four features of the parallelogram are the same, but we've added these two features about the rectangles, which just happen to be, getting kind of crazy here, just happen to be the opposite two features of the rhombus. The rhombus took these two, and the rectangle are taking these two. So a lot of these work together. These four features here keep repeating themselves over and over again, but we're picking up different features per shape after that. Okay, let's do a little bit of SOL practice here. Keep this page close so that we can reference it. Let's check it out. In rectangle PQRS, the measure of angle 1 is 50. Let's find the measure of angle 2. All right, so let's think it through here. We have this 50-degree angle. I like to use symmetry as much as possible. So if this is a line of symmetry cutting through the shape, that means whatever angle 2 is the same as this upper part of angle R, which means we have an isosceles triangle. Well, you've got 180 degrees in a triangle. We've used 50 of it for the given angle, which leaves us 130 to split between these two equal angles. So split it up, and that leaves you with 65 degrees per angle using that line of symmetry. Okay, let's try another one. In rectangle ABCD, what are the values of X and Z? Y and Z. All right, so check out where Y is. Y is sitting in the alternate interior angle position to 35 degrees, and we know that alternate interior angles are equal to each other. So this is a simple solve. Divide by 7, divide by 7. Y is equal to 5. Okay, to find Z, I might use this triangle here to find Z. I know that a rectangle is made up of a right triangle. I know that there's 180 degrees in every triangle, and I've already used 35 for the given angle, 90 degrees for the right angle. So whatever is left is going to leave me angle Z. 180, take away the 35 and 90, leaves me with 55 degrees for angle Z. You guys, there's lots of ways I could have explained that. I'm just explaining the first thing that my eyes see. Let's check out this next one. In rectangle DEBC, EB is 12, CB is 4. What's the approximate distance from point E to C? Well, they are kind of hand delivering the Pythagorean theorem to you. What you need to know is that this right angle creates a right triangle. And if you're going to have a right triangle, Pythagorean theorem and right triangle trig, SOHCAHTOA, is something that you may use. This is an opportunity for Pythagorean theorem. A squared plus B squared equals C squared. I can use 4 for the A value, 12 for the B value, X for the C value. Take a moment and solve for X. Okay, I finished my work here. I squared the 4, squared the 12, added them together, got 160, took the square root to solve for X for a total of 12.65 rounded. It's approximately 12.65. All right, let's try one more time, or two more times here. What is the value of X in rectangle DEFH? Check out where X is. Think about what you know about rectangles. You know that their opposite sides are congruent. So this 25 is kind of a distraction here. It's not something we need. We need the 29. The equation to solve is 3x plus 5 is equal to 29. Subtract the 5. That leaves you 24. Divide by 3. That leaves you with 8. Value of X would be 8. I love this last example. It really makes you think. So let's think through this one here. It says, in the given diagram, what is the measure of ABC? Our X is here. Well, we're using sort of a rectangle and sort of a parallelogram. So I know you've seen this problem before. I've talked through this problem before, but I thought I'd change it up just a little bit here. For the rectangle part, I know that this is a 90-degree angle. So this complementary pair right here has to add up to 90. I've already used 46 and part of that, so I have 44 degrees left for the other part. That's the rectangle piece. Now, the parallelogram piece is, if these two lines are parallel to each other, highlighted in blue here, these are parallel lines, then one obtuse and one acute are supplementary. These are called consecutive interior angles. And the consecutive interior angles have a sum of 180 degrees. So I've used up 44 for the acute angle. Whatever's left over, which is 136, would be the obtuse angle. So that's a combination problem. Now, I explained that differently when we saw that problem earlier in the unit. So if you want to see a different explanation, go back to the parallelogram lesson. Here, I'm using a different pattern to get to the same result. You guys, if you need anything, let me know. Come find me. Practice on your IXL, or I have plenty of paper examples that we can pull out as well. Happy studying!